Hi, everybody. Thank you for coming to the seminar. My name is Maria. I'm coming from QT, from the School of Maths. I did my PhD actually here at UQ in the School of Maths, and I did a bit of traveling in Europe and working in different places. And today, what I would like to talk to you about is something that probably tries to combine together all the experiences I had in my career in one coherent framework that I am now developing. So I'm a DECRA fellow, and this is my DECRA project. So I am about midway through my fellowship, and what you will see is the thought experiment this whole thing started with, some results we already have that have been submitted now, and some further developments that are still very raw and very open. So there's not much has been done there, but I will just show you the idea and I'll try to convince you that it's going to work at the end. You'll just have to believe me that that's all. All right. So I also would like to acknowledge traditional owners. So this is work done on QUT grounds, and of course we pay our respects, just like Bruce said. So where am I coming from? Originally trained as a game theory person, but in mathematical department. I was just learning game theory. But then later, as I was progressing through my career, I was more and more attracted to the idea of social dilemma. And that's probably the most well-known example of a game theoretic issue, because that's the most exciting one. It's the one that everybody can relate to. So you have a problem that you're facing together as a group. You will be better off if you all cooperate together, but there is a huge cost to cooperation. And so you can actually benefit by free riding if you hope that everybody else does this good deed, pays the cost, and you just get the benefit of this good, the good actions that the others did, right? So this is exactly the problem that we're trying to model, and there are many different dilemmas that one can look at. And applications are abundant across animal kingdom. It starts anyway from unicellular organisms, right, like in biofilms. It goes all the way up to human society. So this is something that is still a little bit puzzling. So of course, for decades, people have been paying attention to this, and we know some mechanisms for why cooperation will evolve, even though it is very costly. But we still try to understand why sometimes it's unraveling. So we know that in this situation, we should have cooperation, like there is a mechanism in place that should happen, but it doesn't. And sometimes it doesn't happen for small reasons. So some reason might even not be looking like it's something major, like a major issue, but it still will unravel your cooperation down the track. And that's the thing that I will be trying to convince you about today. So my main question here is a conservation decision-making problem as a social dilemma. Of course, as a thought experiment, I'm using this, but it doesn't have to be conservation. It can be anything where you see this conflict of interests in the situation. Why I'm using this one? Well, let's just look at it because it's kind of easy to relate to, I guess. So first of all, we all like animals. We like them to be in the wild. We like them to be on grounds. Australia is a wonderful country that really supports the native fauna, tries to protect the native fauna. We like to go and see them in the wild. And this is a platypus swimming there. And because I'm not a field ecologist, I don't have many beautiful pictures. This is just a couple. But I do have some where you can demonstrate the idea. So this is my friend coming to Australia to touch a koala because this was her dream. She was really looking forward to this for decades, and she could finally come and do it. And she was so happy that she was able to. Okay, so that's the kind of positive impact I'm talking about. Now, how is this a dilemma? Of course, there are things that we always have to keep in mind. So first of all, we eat, and there are lots of us. So we fish. We fish sometimes species that are more influenced, and then there's also a lot of waste from the product. that we are consuming. And like, for example, this is Christmas markets, and I don't think any of this fish was eaten. I was actually walking around just to watch, just to see if this was done by the end of the day. No, most of it went to waste. We also need to grow stuff, and we talk about organic produce these days more and more. And organic produce needs more area, and so it basically is more impact on the environment. And then we replace koalas with cows. So here's the exact evidence. So you have this positive impact of conservation and ecosystems being there and native animals. And you also need to just simply go by and make economic decisions and somehow make it work. So in many also problems in conservation, evolutionary adaptations are a little bit ignored these days. So I have to withdraw this statement and make it a little bit softer because there's more and more now information coming in that is based on genetic analysis and bottlenecks and trying to make sure that species that are overbred and species that have very poor genetic pool that they are being restored and so on. So there's a lot of support coming in, but the decisions are still static. There is a good reason for it because we simply don't have the data. We just simply don't know how they adapt, how it's happening in time, what they're reacting to, how they're reacting to it as well. So what I'm trying to convince you here is that it is important, and maybe we don't need the data per se. Maybe we can use a thought experiment already in the beginning and try to use this information that we have from evolutionary literature and try to make our decisions a little bit more grounded in how ecosystem adjusts to what we're doing to it. And the idea here is that you may have different speciation events, and then the question is which track you're taking in terms of your effect on the environment, and then you may try to think which one would have higher impact and so on. So this is more like what I would like to do in the future, but so far let's start simple. My close collaborator, Joe Brown, he stands behind the idea of Darwinian dynamics and key functions in this literature of adaptation and evolutionary modeling. And his main argument is always that nature is not an art gallery, and species are not masterpieces. They are evolving, they are adapting, biologically, evolution. So we have to somehow correct our decision making for this. And this is exactly what we try to do in this project. So there are several layers, of course, because we know that you can impose a government or some sort of mediator that imposes policy on the process. And then this affects the ecosystem, but this also affects the stakeholders that are involved. So this could be farmers, this could be fishers, this could be NGOs that are making decisions about conservation. And this whole thing is interacting together. It's not separate layers. These are layers that are interconnected very closely. And there's always also a question whether objectives that they have are aligned or not. So you know that the ecosystem is adjusting, it wants to survive, it wants to propagate, it wants to just live. And then the fishers are trying to fish them, and the objectives are obviously misaligned. And this is just the simplest example. This, of course, can get much more complicated than this, like NGOs want to promote the ecosystems living there. And so let's see how we can think about it in terms of a framework. So this may be important when we're talking about, so one argument when I talk about this to people, one argument I hear is, first of all, that ecology is much faster than evolution. So evolution doesn't matter because it just happens much slower. And decision-making for timelines are so short that there's just no time to react to evolution. There's nothing that can happen in this time period. But by this point, we know that that is not true. There is rapid evolution, and it often happens when there's really high pressure environment. So if you really disrupt it, if you really cut aggressively the forest, you will cause rapid evolution. And this is just one example that was published last year of a rattlesnake. So unmanaged population was just mildly poisonous and rather large. And then there was a managed population on the island, and the islands were shrinking because of the water levels and the cutting of the land. And the rattlesnake evolved to be smaller in size and more poisonous. So the venom was more potent. And this posed a bit of an issue on the local ecosystem that was on the ground that they were feeding, were evolving with. So there are several ways the manager can think about it. So a manager can just ignore this and just reduce the reserve size and just because that's what they need to do. They need to use the land for some reason. So they cut it. And another thing they can do, of course, is they can account for ecology. So they account for population size change. So they may try to think, okay, given the underlying ecological process, given the population dynamics, we can try to adjust our decision and predict what will be the population size and whether they will flip into extinction, whether they will die at some point. So we'll try to make sure that this is something we account for. And the last one in this case would actually be a little bit more advanced and thinking, okay, we're cutting the reserve. What can they do in response in terms of adaptation? So you can try to predict a situation like this if you know the biology, if you know what they're feeding on, and if you know generally how they are hunting and so on. Right? You may try to then account for this in your decision making, and whether you want this outcome or not, you may try to steer the population. That's the idea. So the idea is steering your population in the desired outcome. And I know it may sound wacky and magic, but let's see how we can think about it in terms of modeling. Let's start with a very simple example. So we have a potential reserve area and just normalized size of 1. It's a status quo, that's how it is right now. A manager decides whether to cut it or not. And there is some species G living on this area. But there is also economic value to this. So they may use it for something. They may build roads, or they may build tourist attractions, or they may just simply build living spaces and so on. So there may be other things there. It doesn't matter what we are. The question here, there is an ecosystem that lives there, and there is the economic value to the land. So to understand this, there are several steps I'm proposing we need to do. So first step is we need to understand what is the underlying evolutionary feedback on this land or this particular species. And for this, there is many different ways one can use. There are many evolutionary models there. One that might be useful in this case because it's a little bit more forgiving, I would say. It's a little bit more flexible. Is something we call G functions. So G functions are basically trying to predict what's going to happen with fitness of species given their trait value. The trait value could be your body size or the potency of your venom in the snake example. And then here, depending on what is going on in the environment, you will have these peaks in the fitness landscape, and the species that has the trait value will try to climb this peak. This is basic selection. So you force them into Darwinian selection, you force them into climbing the peak and finding the best nearest peak they can get. They might not get to the red one, which is the best one. They might just get another local peak, but it doesn't matter. They just always try to climb the gradient that's the peak. And why this is useful? Because G functions actually are not sensitive per se to a specific system, specific species you're looking at. You can actually group together several species that occupy the same niche, for example. They have the same underlying physiology, the same underlying biology. For example, in terms of kangaroo, I think there's something like 20-something species of different kangaroos in Australia. And in principle, you could group them together, so they would have slightly different parameters, but they would fall within the same G function approach, so they could be fitting this fitness parameter. So if you have that, you need to have some sort of underlying ecological model. And the classic, what Terra sort of style logistic growth is simply the case, doesn't quite fit. So it has to be adjusted, because basically what you as a manager need to understand is what's your input, right? So what is exactly the point, the pressure point that you are applying to the cell system. So this paper looked at seagrass in Antarctica, and this is the model that was used to describe the seagrass ecology. And the idea there was that there exists some sort of energy, say sunlight, that they need to live and reproduce. And if the sunlight is too low, then they will just go extinct. So there exists some sort of critical threshold of the needed resource below which they die, and above this threshold they're happy and so on. So there may be other more complicated variations, but for the beginning, let's just stick with the simplest case. We have the model that has two steady states, and depending on where your critical energy is, you're either extinct or happy at the carrying capacity, and everybody's living happily. Now, this is ecology, so how do we make this ecoevolution? For this, we need to assume that this needs to be some sort of trait, right? So like body size, potency of the venom, or just the efficiency of digesting this sunlight, right? So how effective you are at producing the resources you need. And this may depend on some sort of trait U. And this trait now is climbing the gradient of your fitness function. So the fitness function tells you how fast they're growing, the population size, and the trait itself now also tries to climb this fitness landscape. And you also need to ensure that there is some sort of evolutionary trade-off in the model, because this is the way of thinking about evolution usually. So if you make them more efficient at something, they have to pay some sort of cost. So it has to come with a cost. There has to be something there that punishes it, because otherwise everybody would have this already, right? This just the underlying message. So for example, if you grow bigger, if you get a bigger body, your reproduction reduces because you need to grow first before you can reproduce. So your reproduction is then much later. And this is how this evolutionary trade-off comes in. And this usually sits in either the growth parameter or the carrying capacity, depending on the trait you're looking at. And then your critical threshold now also becomes a function of the trait. And in this case, the prediction of the model is really sensitive to how you set it up, which is not surprising because the model is now much more complicated. But let's see what we can get. So if, for example, we assume that our reproduction decreases with the trait, so for example, its body size, you get bigger, you produce less, and your carrying capacity stays the same, this would be the behavior we want. So you have still the extinction, you have the threshold of the energy, and then you get this smooth growth in the population size, depending on how much energy they get from the environment. This is just one example. There may be many others, and I will show you another one later in the slides. Okay, now, once we know how we look at the ecoevolution, of course, as I said, this is just a thought experiment. You may need to do a little bit more to understand what's going on underneath the hood. But another step we need to do is to understand the actual game. What is going on? So there are many different models in game theory that one can look at, but this one in particular that may be considered a little bit more useful in this case. We call it Stackelberg evolutionary games. And the idea here is that you have some sort of followers, for example, the ecosystem that is evolving, and then you have the leaders who are deciding what sort of condition imposed on the follower. And the follower then responds with population size or trait value, whatever they're doing in response to the environment. So the way you impose the conditions on the ecosystem, you choose the energy they have available. So for example, you give them reserve sites, or with the seagrass, you put them in a place where there's more sun, where there's less sun, you cover them, and so on. So there are many different ways to manage this. And this approach was used in cancer. It's quite successful in cancer. It quantifies evolutionary therapy in cancer. There were some attempts to apply it to fisheries, but I think for fisheries, this might be a little bit difficult because there are many other moving parts in the problem of fishing. And there were also some attempts to put it to pest management. And I think for pest management, this might have quite a bit of benefit, because the main idea here is what you're trying to do is you're trying to manage the ecosystem. You're not trying to make them go extinct. Sometimes it's just not possible, especially with pests on large scales. You just cannot possibly eradicate them. So what you want to do sometimes is you want to keep them under some sort of control. So that's a control problem that Stackelberg can do. So you're trying to impose a control on the ecosystem and keep them in the safe parameter space where nothing else suffers and nothing else goes extinct. So here I'm trying to now think about this as a first layer of this problem, where you have a policymaker and the feedback from the ecosystem, and you use a Stackelberg game to evaluate. How do you do that? So you need some sort of objective function for your policy. Like there may be many. This is the simplest case you can imagine. You have some sort of economic benefit. There's some sort of price on land or forest that you cut. And then there is also this intrinsic benefit of ecosystem being there. So you just care that they're there. And in this case, what your function is dependent on is the size of the population. So you just want them to stay there and not go extinct. And this enters your objective function. So you're trying to maximize now the benefit from getting them there and keeping them. And what can happen if you then apply the analysis of a Stackelberg game and look at the optimal leader's decision? In game theory, we often talk in terms of best result. So you're trying to find the best way to control the population. And because it's now a sequential game, because I am as a leader, I observe the ecosystem, I know what sort of reaction they get. And then I try to impose the decision-making process knowing this, right? So it's a sequential decision-making problem. I'm a leader and I'm controlling it. And so here I can actually try to get the best output from the system, knowing the best response. So the best response is this black line that depends on the energy level in the system. And for this particular objective that we looked at, that only depends on the population size, it actually doesn't matter that you can make a decision first. In this case, it's absolutely identical. So whether you're doing it sequentially or simultaneously, you will arrive at the same decision, that is just the intersection of the two best responses. Oh, sorry, the green one is the species and the black one is the leader. Best response. And so now, okay, we know the ecosystem evolves, and your best decision is to cut about 50%. They will be fine, they will survive according to this model. And then you will get some sort of 50% benefit of the land. You will build something on it and so on. So overall, not so optimistic, right? So 50% land is gone and we are doing something else with it. Well, let's think about it a little bit deeper. What if we can actually start caring not only about the population size per se, but also about the trait itself? So for example, Australia has red kangaroos, and they're big, and we want them to be big because this is how they are, and we want them to preserve to be big. And if we start cutting the land, they might evolve to become smaller, and we might want to prevent this. This is just one thing, one simple example, and I'm sure you can think of many more complicated and more interesting ones. It's just simply not my field. But the idea here is, imagine now you want to start caring about the physical or biological features of the population you're managing. And then suddenly the decision prediction changes. And so now as a leader, you can start to want this best response of the species, and you can do it because this is a sequential decision-making problem. So if it was simultaneous, we would be sitting here, cannot do anything better than this according to game theory predictions. But now, because you are imposing decision first, you can force them be here. And if you do that, you will actually get a really high payoff. So this is the payoff of the decision maker, and this is the problem without the trait, and this is the problem with the trait. So if you care about the trait itself and you want to optimize the trait and population size, you will actually cut only 10% of the land. So here, the benefit of trying to accommodate biological and physical features will come handy in terms of how much space you give to the ecosystem. There are also other things you need to consider when you're looking at a population, and especially in the evolutionary frameworks. What we usually talk about are frequency dependencies and density dependencies. So evolution can be frequency or density dependent. What this means? Density dependence, Lotka-Volterra. That's the density dependent model. You have competition, you have carrier capacity. It's just about how many of you are occupying the carrier capacity. Now, frequency dependence, if you add that in, it's all also not only about how much of the carrying capacity you occupy, but also what's the benefit of other traits around you. So suddenly it's not only about just being there, it's also about responding to the environment. So one example is you can have birds arriving in the place to breed, and then depending on when you arrive, you can arrive earlier or later than everybody else, and there are benefits and costs to both of it, right? So if you arrive early, you get the place, but it might still be cold. You might just not benefit from this. Your eggs might die while you are laying them too early. If you arrive too late, there's no more ground for breeding, and you will be in trouble looking for it. So this is the frequency of that, right? So depending on what everybody's doing, you have to also adjust. And if your system exhibits frequency dependence, things get even more complicated. So instead of now just having this one extinction threshold and then line going up, depending on how many traits you have in the population, you will have different landscapes for the fitness function. And then this will also mean the biodiversity richness. So if you are in this status quo point of 1, so this is where you start, depending on which line you are starting, if you go down, you will start losing biodiversity. So the first one you lose, between 4 species, you will lose 1, then there will be 3, 2, and 1, and then 2 and 1, and then only 1. It may look like not a big deal, but the problem is what we call in evolutionary theory as overstabilization. So if you drive your population, so remember in one of the predictions, our cutting was somewhere here, 0.5, right? So you cut it 0.5, so you either have 1 or 2 species being preserved. And then the question here is, well, are they actually having the capacity to adjust? Because the answer here is no, because now this whole richness is lost, and all the evolutionary paths to stability are also lost. So you would have to make sure that you preserve as many as possible, because in this case, only the top line is the evolutionary stable line. So you would have to try to make sure that you preserve as many as possible of the phenotypes or species in the population. And you get there by accounting for the trait in your objective function. So objective function that cares for the trait itself will land you somewhere here. And this is, and this is what we will see in this one. So we have these 4 different lines that species are responding, and we will only get there if we care for the trait and the population size, and then we'll only be cutting about 10% of the land and preserving their adaptation behavior. Yes, that's the idea. So you're trying to convince the manager that maybe it's not only about the genetic variation per se, you don't really need the data per se. What you need the data about, not the DNA analysis, you may just want to observe the traits, to see how the traits are changing, what's going on with their size, what's going on with their metabolic rates and so on. So something that you can actually see can be already helpful when you're trying to manage an evolving ecosystem. Okay. So once you know this, and this is already a game theoretic problem, even though it's more of a control problem, like it's not per se a game theory problem. You can make it a little bit more game theoretic once you start thinking about these stakeholders that interact. And this is the higher order game, as I call it, but this doesn't have a name yet. So this has been submitted. Everything coming from this point is still very much raw thought experiment. So if you have multiple decision makers, now imagine a situation like this: same reserve size and species, but they have now split the area. So there's one decision maker in one corner and the other decision maker in another corner. And they together need to decide how much to allocate to species. And the species doesn't care whose patch it is, right? As long as they have the patch where they can live, they have. So what we can do, we can crudely, from these payoff functions with one leader, reconstruct two leader payoff functions and frame it as a game. So in this case, cooperation means that you give the species the required half of the length that they need. So for example, here, you would give them something like 0.8 or 0.9, so you would have to give them 0.4, and that's cooperation. If you don't, that's defection, because basically then the other person will also not, and then the species acts. And if you do that, you can compute the payoffs from all of these processes and evolutionary adaptations and so on. What you get is a coordination model. You have two actions that are constituting two pure Nash equilibria. You have cooperate, and defect. And in this case, cooperation is risk dominant. So for this evolutionary scenario, with the leader caring for the trait, if you have two leaders, you're still somewhat safe, right? So two Nashes are a problem, but given that the other one is risk dominant, it's not such a big problem. So it means that they would prefer to cooperate. So they get technically a higher payoff here. Now, this is, of course, assuming that there is no like undercutting, no dynamic, no bargaining, so none of this complicated stuff that actually happens in life. So just a very simple scenario of simultaneous decision making. Now, what can, even in this simplest case, what can affect your decision making is just simply the information. So as I said, whenever I talk to an ecologist, they ask me, well, how are you going to just fit any of this? This is just so much data that you need. And so we don't have this information. This is not there. It's not present. So how do we deal with it? Imagine you have this scenario one that we already looked at, where the evolutionary trade-off is such that reproduction decreases with you and carrying capacity stays the same. And then you have a second scenario where it's quite the opposite. So you have reproduction increasing with you and carrying capacity decreases. So now your behavior of the model qualitatively maybe not too far, but it still has this extinction. The threshold is much lower, and then it goes up. So this scenario is much more positive, right? So you have this lots and lots of control that we can do until you actually drive them into ground. So before, we didn't have so much for that. We know that at some point they will die, and you might want to avoid that. Now imagine we know that maybe this is the evolutionary scenario. This is what they adapt like, because adaptation is usually positive, right? They become better at what they're doing unless they hit the ground. This is the trait of their face. And so you are here. You are at point one. You don't know which one it is. In principle, at this point, they're somewhat similar. Both of them have some population size. You may say, okay, just depending on the parameters, maybe my parameters are not quite perfect, but both of them have a stable population size, and we should get it done. So the question is, as you start cutting, where do you get which one is it? If you want to just separately calculate the payoffs from these two problems, the second problem now is a prison's dilemma. Because of all this permissiveness from nature, because it's so adaptive and very good at it, you actually want to drive them to the ground because it's just not good for you to operate in the And then the question is, okay, what if we don't know? Maybe there's a nature that just throws a coin. This is the simplest case you can imagine. Of course, there are many more complicated scenarios you can form. You can talk about beliefs. You can talk about many different layers of interacting. But the simplest case, imagine there's a coin, nature flips it, and then inside the scenario 1 or 2. Then, if this is the game, then we have a coordination game, and now defection is dominant. So any permissiveness in the ecosystem would lead you to less friendly to the ecosystem decisions. And that's something that comes up even in this very simple scenario. And I'm pretty sure that once you start building more and more sophisticated mechanisms around it, you will still observe a similar trade-off, just with a little bit of more bells and whistles around it. So, okay, now I'd like to conclude. First of all, I try to convince you that conservation is an eco-evolutionary problem. It's not just ecology. There's a lot of adaptation going on, and we have to adjust for it and make part of our decisions. And the trait information might be used as a proxy for your evolutionary adaptation. That's my argument. It might not be perfect. Most likely, in some cases, it will be very wrong. But in most cases, I'm pretty sure it will give you some information about the underlying evolutionary adaptation. And this sort of approach with leader-follower games, Stackelberg approach, might be a natural way to think about it. It's not that complicated. It's quite simple. It's just a control problem where you're trying to steer your population in the direction you want them to take. And the one thing that is very important is the objective that your manager has. So if they don't care about the trait, then none of this will work. So they have to make sure that adaptation, evolution, trait is part of your decision-making process. The one thing that we are thinking about and trying to develop is thinking about a safe sort of area where you don't know perfectly where they are, what the equilibrium are, but you're trying to steer them in the safe area where you know that even if you are off, they will still be fine. Like there's some kind of epsilon all around this area that you're trying to steer them in so that you can balance this evolutionary trait. So we're not trying to prevent the evolution, but we're trying to anticipate and steer the reaction, right? That's the main idea. So we want to understand it and make it part of our decision. And I stop here. Thank you so much.